Hello everyone, we are group 36 in this CS1231 module. I'm Qian Peisheng.
I'm Baichuan.
I'm Huang Bohan.
I'm Zhou You.
Our topic is mathematical gaming. Specifically, we have chosen a game Trapping the Cat. First, I will introduce the background and rules for this game. Next, Bohan and Baichuan will demonstrate how to play the game. They will also explain the mathematical properties of this game. And next, Zhou You will provide some further questions related to this game. Now I'm going to introduce the rules for the game. There are two players in the team, namely human and a cat. The game is played on a designed chessboard with a finite number of blanks. There will also be 7 to 18 preset barriers randomly settled on the graph. The object of cat is to move outside of the chessboard, while the object of human is to block the cat with barriers before the cat go beyond the boundary. The cat can jump one step each time to an adjacent empty blank, while the human can set up a barrier on a blank each time. The winning condition of a cat is to reach the boundary of the chessboard before it got trapped, while the winning condition of human is to prevent the cat from escaping from the chessboard.
Hello everyone, we are Huang Bohan
and Baichuan.
We are going to demo this game for you. For this demonstration, we are using the following website, trapthecat.org. It is a free website and you can play it in your free time.
So now I will demonstrate the first and the second round for you.
And I will demo the third round.
The chessboard has 11 staggered rows, and there are 11 grids in each row. At the beginning of the game, there are several randomly pre-allocated barriers in the chessboard. The cat is in the center of the chessboard. When the game starts, the human can place the first barrier. Now, let's start the first round. Usually, if we want to trap the cat, we tend to put the barrier near to the cat. Now, let's try if it works. So, I put my first barrier next to the cat. Then the cat moves up. If I still put my barrier near to the cat, we can see the cat keeps moving up. So the church near to the cat, there will be at least 4 directions that cat can move to. So there will always be a path for the cat to head to the edge of the chessboard, and then it can escape successfully. Let's try another round. We put the barriers 1 grid away from the cat. See if it's enough to trap the cat. We can see that there are still too many directions available for the cat to move. Therefore, we need to set the barriers at a longer distance from the cat at the first place. The truth is, if we put the barriers too close to the cat, that cat will definitely move to the opposite direction from our previous barriers. So, the barriers we set before will not be useful in the later game. In another word, if we set our barriers far from the cat, later those barriers might be useful, blocking the way when we try to push the cat to that direction.
In case that you don't believe my method is correct, I will demo again. This time we only have 4 pre-allocated barriers, so it will be quite a tough one. I think I should start from this direction. So we move to this direction, and then I should do this and this. So now you cannot go to this direction anymore. Now you cannot go to this direction, and you can only move to north or east. Now you can only move to the east. So you see, we have successfully trapped the cat again. From the experience of the last few games, we know that in order to trap the cat successfully, we need to place the barrier 4 steps away from the current location of the cat. But sometimes if we can make use of the existing barriers, it can be even less than 4 steps. Analyzing the map, we know that in these 2 directions, there are few pre-allocated barriers, so we need to enhance our defense here. I place a barrier here. And since it moves to this direction, I place another barrier here. And here. So now we can see that it has come to the trap we set for it. Once I place the barrier here, the cat cannot move in this direction anymore, and it can only move to the other traps we set for it. Now it can only move to this direction and this direction. I keep on put barriers. So now we have successfully trapped the cat.
Hello everyone. In my further discussion part, I'd like to talk about 2 things. First, whether there exists a number that is the smallest step required to trap the cat. And second, I want to introduce 3 theorems that we discovered from this game.
The first question we want to discuss is, theoretically speaking, what is the minimum step to trap the cat? After our discussion, we find that the result is surprisingly simple. The minimized step to successfully trap the cat is 1. Let's see why it is 1. Before our discussion, we must first assume that the barriers generated first is strictly random. At the opening stage, we mark the position around the cat as 1, 2, 3, 4, 5, and 6. It's quite obvious that when there are 5 or 6 barriers around the cat, only 1 step is enough to trap the cat. For example, if position 1, 2, 3, 4, and 5 are the barriers, you just click position 6, then we are done. If the 6 positions surrounding the cat are all barriers, since human is the first one to move, you can click anywhere you want. The result is the same. So, the theoretical minimum step is 1. Perhaps the more interesting question is, what is the probability of appearing such ideal case? Let's calculate the probability. First, we assume that across the board there are 81 positions. Every time before we start, 4 to 20 positions of the range were set as barriers. By the way, there may be more or less. The calculated average number is 12, as the position where the cat sits cannot be set as barriers. The initial position is that 80 positions can be set as barriers by random. We assume that the probability of each position being barrier is the same. If the 5 positions surrounding the cat is set as barriers, the combination of 12 barriers out of 80 per point is C1280, which is 60,246,643,120,300, with science count method set for 6 times 10 to the power of 13. Now let's calculate the possibility of 5 out of 6 positions are marked red. In the 12 red points, the combination of putting 5 dots at the position 1, 2, 3, 4, and 5 is 6 times C5 12, and the result is 4,752. So the probability P5 is approximately 0.8 times 10 to the power of minus 10, which is 8 out of 10 billions. In other words, if a country has a population which is 100 million, then all the people in the country play this together, and each people play 10 rounds. There may be one case that 5 positions around a cat are barriers. The probability of all 6 positions around a cat are barriers is P6, which is 1.54 times 10 to the power of 11, which is even less. Now I will introduce what theorems we have discovered in this game. Theorem 1. If you see the barriers which the distance is less than 2, unless you have a very good terrain, or the cat will run away from you. So in the opening stage, you'd better put your barriers which distance is greater than 2. Now let's see why it's like that. In this situation, suppose the cat aims to move to the upper right since it's quite open and empty. If you set the barriers at 1, then the cat will move up to 2. Then you set the barriers at 5, the cat will move to 10. It's obvious that the cat will all walk away straightly to the upper right direction. If you put it at 4, the cat will still move to 2. If you set at 5, then it is the same as the previous situation. If you set at 10, the cat will move to 5 extra, so it will not work. However, if you put it at 7, then it's different. The cat is at 1, you are at 8. The cat is at 5, you are at 11. Then you block the cat because you force the cat to turn around. So we can see that if you see the barriers which distance is greater than 2, it's more likely that you will trap the cat. Theorem 2. When you see the first barrier at the opening stage, a blockade line will form between you and the cat which is closer to you. What you should do is to try to let the existing barriers and the barriers you want to set lines on the blockade line. In this picture, the red barrier represents the starting point of the cat. The green block represents the first barrier you set. The numbers in green represents how many steps that the cat actually needs to reach there. The number in red represents how many barriers you need to form a chain. Obviously, if the number in red is less than the number in green, it means that the cat will be faster than you to reach this place. Then it is meaningless to set the barriers there. And what the blockade line does is exactly the positions where the number in red is just greater than the number in green. This diagram actually tells us that when you set the barriers, you'd better not too radical. Instead, you should try to put the barriers on the other side of the blockade line. Theorem 3. The cat is greedy, so the barriers you put must be in front of the cat. In our testing, we observed that the cat applied the greedy algorithm to make each step, which means that the undercurrent situation, it will only move to the direction which contributes to the most to the escape. Notice that it is always based on the current situation. It will not play friend. It will not have a long-term plan. So the cat is actually predictable. We can take this advantage to set the traps. We leave one direction and let the cat move to that direction. Meanwhile, we set barriers on all the other directions, so we can trap the cat in this last second.
That's all about our video trapping the cat. Hope you have enjoyed it. Thank you for watching.